Hello, this is the video record for the practical exercise number 5. We are also going to work on it in class as well, so probably this is ultimately the most difficult practical exercise where we will have to create our own neural network, train it, and everything relying as much as possible on our own functions. We might probably just not use the gradient descent function, however, it is also possible to use that as well, just as we did in the first practical exercise. Instead, we are going to rely on the familiar for us already minimize function. But really, that is it. All the other parts are accordingly on us, and we have to do everything else. So in this practical exercise, we are going to classify the images of the pictures. So basically here you can see example of different digits handwritten, and our task is to recognize what is shown in this picture. So as you can see, some pictures, some digits look similar, some really not, and still it's possible to achieve quite high accuracy and, well, maybe not the best possible, as we will see later on. Convolutional neural networks can be better in this case, but still, considering how simple this neural network can be, it's actually quite remarkable result. So let's see what's our task to do. So in this practical exercise we are going to have some minimal individual parameters such as regularization parameter and the number of neurons in hidden layer of neural network. So as we discussed in lecture, there is actually a hidden layer here that's connected with all the other neurons, and accordingly the connections are specified by the theta parameters, theta 1 for this layer input and theta 2 for this layer output. So accordingly, together, if we use all of these layers and all of these theta parameters, we can calculate the hypothesis as the output of this neural network. We are going to use just sigmoid activation functions for today, but eventually we are going to try some more advanced functions. Additionally, I have provided some helpful code for you that you can copy and use some functions which are maybe not so important to understand exactly how it's working, but still, if you will have any questions, I'll be glad to answer specifically about any part of this code, since I wrote it myself. So basically I can explain whatever is not really clear for you there. Also, I will comment a few things as we go, and I believe we can start. So as you can see here, I have done some formatting, and actually it looks almost as if the final report. Actually, I can even show you how it will look after all the calculations have done. So in fact, you may consider to putting some formatting work in these interactive Python scripts, yes, so that you can simply then export this as PDF, and basically this is how this looks like a report. So you can say print, yes, just check if everything looks okay. Sadly, there is no way to remove this show code, but it's still good enough. So accordingly, changing some margins and stuff like that, you can make it look a little bit better. So it's possible to simply make these reports. However, in that case, please don't forget to add your name, surname to the report, so that I know who are you. You can see more explanations about this stuff, how to make such things, in the practical exercise video record 1, which is probably not yet available, but it's going to be, so you can study that as well in the formatting part. So today, however, I'm going to start with a blank file with some text and tasks that we are going to do. So the first things first are actually loading the data file, of course, and displaying some random pictures. So there is a total of 5,000 of different pictures. So basically 500 of each digit in this dataset. So we are going to pick randomly 100 of them and display them. So I don't have this data file yet, so I'm going to upload one now. You can download this from Ortus. So the file name is digitdata.e. E means that I have edited it a little bit to better match our specifics in Python. So the task 1 is, as I said, display some random images of this dataset. Then we specify additional functions such as sigmoid, sigmoid derivative, then packing, unpacking functions, and so on. Then task 2 will be to actually implement the neural network itself, so its normal operation, feed-forward mode. So here are some formulas and details I will use as we discuss. Then task 3 is to implement backpropagation function and gradient estimate, which is necessary for us to actually perform the training of this neural network. And of course we also need a cost function, including the regularization parameter, to be implemented. Putting everything together, then we can run our minimize function to find these theta1 and theta2 parameters. Well, it's actually entire matrix of the parameters now, and to test how successful our neural network training has been. So in this practical exercise example, I will show you lambda parameter 0 and minimum number of neurons of 25. So it is probably a good idea for you to actually follow this along, and once you see for certain that it's working, then you can change to your parameters. Also, as we speak, I will show some ways to making sure that we are in the correct way. So we are going to check some functions as we go. So let us start from the very beginning and include all the necessary packages. So let's move this a little bit here. So we are going to use numpy as usually for data type. We do not need pandas this time, however, because we are not going to use pandas data type. Then we are going to plot some confusion matrix. That means we need seaborn. Then we are going to plot some plots, yes, so we need pyplot. We are going to generate some random indexes as to which of these 5,000 pictures are we going to show in this plot. Yes, so we are going to choose them randomly. So for that we need random integer number generator. The data file, as you may have noticed, is in the MATLAB data file format, MAT file. So Python is completely fine with working with such files as well. So we need SciPy input-output library to deal with it, as well as uniform distribution from the statistics package, minimize function from the optimize package, and also some additional functions such as training, testing dataset splitting function, confusion matrix from a sklearn matrix, and finally we are going to use a built-in function to convert the labels from 0, 1, 2, 3, 9, yes, to the categories, making one hot encoding by two categorical function which belongs to the keras package. Yes, so this keras package is actually quite important for us in future, so it's first time we actually deal with it. Now, if you want to be able to actually collapse this code, you can specify this by this specific type of comment, yes, of this label. Or markup, or how it is called correctly, title, and even more so, whatever is written afterwards will be seen. You can actually even format it as you see fit. So for example, I can make this in bold. Oh, sorry, that is italic. In bold it would be double, like so, yes. If you know HTML, you can actually even set this as an HTML. So again, as I said, that is all in the first practical exercise in more details, but this is valid. You can put HTML tags, you can put some latex markup language and all the other stuff like so to actually make your text look better. So okay, I'm going to use my benefits of having the second screen, so I'm not going to type in this. However, I'm also not going to rush it, so I'm going to be slow and consecutive. Yes, so the first thing we are going to do is to load the data file. So we load the MATLAB data file by using the function loadmat belonging to SciPy input-output package. So it is as simple as that to specify this MATLAB data file. So MATLAB stores its variables in something called a dictionary, meaning that it not only contains the values but also the names of the variables. And in this specific data type I have two arrays. One is called x and another is called y. So they are called specifically like this, and in order to read them you have to know their names. Well, actually it's possible to read them from this dataset part, yes. So if I run this, it's going to connect, yes. Dataset, dictionary, yes, and as you can see it mentions that there is an array of x and array of y, so you can read that information from this variable easily. So that means that now we have to extract from this dictionary our data types x and y and create numpy arrays. Yes. So in order to extract x data, I'm going to need to read the data set in the square brackets x, where x is the actual file name that is inside of this dictionary here, and this x is whatever data I care to call it. Yes, so this is the name I choose to use. So it's logical to actually use the same one as in the dictionary here, and we do so for y data as well. Yes, so that is y dataset y. So x in this case is the pixel colored in grayscale from 0 to 255, yes, as an integer number, whereas y is the digit itself, what is pictured in this image. Yes. So we start then with specifying our input parameters such as hidden layer size. So I choose 25 as a number of neurons in hidden layer. So specifically in this layer in between I have 25 neurons excluding this bias. Yes, I'm going to add this bias later on. Then I also need to know how many inputs do I have in my neural network. However, I can read that from this dataset X, yes, because this is the number of pixels our neural network is going to have at input in order to make a decision. So we are going to use a function called shape. Well, it's a function but actually a property of the X data type to read how many rows are there in table and how many columns. And the number of columns is the number of pixels. So each picture is unwrapped into one long vector. It's not a two-dimensional picture here now. It is now just one long row, which consists of 400 pixels, 20 by 20 to have this as a picture. Yes, so accordingly we are going to need later on this m and as well as this number of inputs multiple times as we will train our neural network. Similarly, we need to know also number of the outputs of our neural network, which is the number of the unique labels y. Well, we know for certain that this has to be 10 because there is no more digits like 0, 1, 2 up to 9, total of 10. However, it's still better to actually make sure and ask Python to read what is the list of all the unique labels and how many of such unique labels are there. So if I run this now, this will produce me the output, which is now I'm going to hide so that it's, you know, looking more compact. So the task one is to display some random images, and for this purpose we can use this function I have provided for you. So first let us copy this. Hopefully it copies well from PDF. Well, actually no, you have to, you know, put some new line symbols. So I'm going to copy from another place here, which I happen to have. You, however, will have to compare with here and actually add some new lines, yes, or use some more advanced editors which can actually replace the new line symbols. So what is happening here is that now we are going to create an array of pictures, like 10 by 10, and some sort of a matrix, yes. Instead of elements, however, we are going to have an image as each element, and for this to work we need to implement a function called subplot to grid, yes. So basically we specify how big is our grid, and then we iterate over it, starting with I, then going by j, and so forth, yes. And this reserves the position in the picture to be displayed, and according to that reserved position we call the function image_show, that is displaying the picture. However, our picture is not a two-dimensional picture, so we have to reshape it, yes, to make it from 400 long row into a matrix 20 by 20 pixels. And furthermore, in order for this picture to look like not rotated, we have to specify the parameter f as an order. So I would recommend you to study more of this parameter, because it can have multiple options, and if I say, for example, we'll have it skipped, yes, then you will see that the pictures will actually be somewhat rotated. And I choose randomly one of the m rows, yes, so as a random integer number. So then I don't want to see any axes, any labels, any stuff. I just want to see some pictures, and I change the color map to the grayscale. So if I run this block now, it should create the picture, and this picture is going to be different each time I run the code. So now I run it once more. Now the first digit is 9, 0, yes, and I run it once more. It is 1, probably 6, yes, and I'm not even sure what this digit is. So you can this way actually see the different versions of these handwritten digits as to how they look, and the task of the neural network today is to actually achieve quite high accuracy of, let's say, 95%, of being able to correctly recognize these images, and this is completely possible. So while we are at here, let us also do some additional stuff, such as divide dataset into training and testing data, as we did already in the previous practical exercise. So we say training, testing, x data, training, testing, y data. We use train test splitting from our original data x and y. We specify the ratio that the testing dataset is 0.2 of the entire dataset, meaning it has 20% of all the data, and the training dataset accordingly will have 80%. And some random state, so that each time we run this neural network, it's going to work with the same dataset. It's also going to shuffle it, randomizing process, so it's going to be good for us. Next, let us also convert this y-train and y-test into a one-hot encoding. Yes, so one-hot encoding, two categories. And for this we are going to use a function toCategorical from the Keras package. Yes, like so. For training dataset, so we simply overwrite it, yes, and for testing dataset as well. So this function has been provided for you, and this is what we have added here. Yes. So the task 1 is complete. Yes, it provides me output, which I keep. Then we need to specify some additional functions which we will require as we program our task. Yes. Well, I have left here some comments for me to stay on track. Yes, and accordingly we did specify the sigmoid function many times, so I'm going to copy this and no, not like this, and paste. Yes, so sigmoid function is calculated according to this formula: 1 divided by 1 plus e power of minus x, just as usually. Now, the sigmoid derivative, as we discussed in our last lecture, is easily calculated by sigmoid function as a sigmoid of x multiplied by complement of the sigmoid, that is 1 minus sigmoid x. Yes, so we make one more function called, let's say, sigmoid derivative. Yes, and we calculate it as a sigmoid multiplied by 1 minus sigmoid. As simple as that, and we return this function value as it is. Next function is also available in this PDF file. However, it will again not be copied as normally, and unpacking also actually is available here as well. So I'm going to copy them from my source. So why do we need to actually do this stuff? So here the idea is that we are going to use the minimize function, and the minimize function will accept as an input of your cost function only vector row or column, just a vector. However, we need to optimize now for two matrices. Yes, each of them has number of rows, each of them has number of columns, so we need somehow to compress them into one long row. So this is called a packing. Yes, so what we are doing here is we convert first matrix into a row, second matrix into a row, and then merge them together into one long row. And of course we will have to reverse this once we do some calculations for cost function, for gradient, yes, inside of these corresponding functions. But for us to be able to work with that, we really have to have one vector row to work with it. Similarly works unpacking function. Yes, well, in actually opposite way, so that now we find what is the number of theta 1 elements from this long vector and how many of theta 2 elements are there in that long vector. We could have theta 3, theta 4, how many layers we have, yes, and this will happen just the same. Yes, however, this will make this practical exercise even more difficult, and it is already quite hard as it is. Probably you might think that it's not that difficult because you have this guidance, but believe me, if you were given the task to figure out everything yourself, you would have a lot surprises here, which I'm trying to mention as we speak, including this requirement for minimize function to have this as a vector, single vector, so you have to merge them. So okay, these auxiliary functions have been created. Now I need to run them to actually store, and now I can go to the task 2 to actually implement the feed forward of the neural network, yes, to calculate the hypothesis based on our pictures. Yes, then we are going to calculate the error and backpropagate that error to find the derivatives, which we are going to need to optimize, that is, to search for minimum of our function. So Here is the short, brief reminder what is performed in which order. So the first thing we need to do is to take our data x and append the bias, that is colon of 1, in front of this x. So this is basically adding bias just to our matrix x. We do not add this bias somewhere here in the beginning because there is no really point in doing that, and it's more convenient to actually do that inside of the neural network. Yes. So the next step is we calculate the output of the first hidden layer here. Yes, these outputs without activating. Yes, so we calculate this as, so please keep a note here that actually in lecture I was using this theta 1 multiplied by a1. However, in this practical exercise we are going to multiply like this for a specific reason. This actually depends on your theta parameter, how we can say, representation. So we can, wait a minute, epic pen, we can specify theta matrix in two ways, and depending on how exactly we specify it, it's going to be requiring you a different order of matrix multiplications. So first, in this practical exercise today, here we are going to specify theta, just a moment, just not to lie to you, to be extra sure, as the number of rows equal to number of features. So here is your data x, and there is a specific number of columns in this x. Yes, which is in our case, as we have named it, input size. Input size. Right? And this is going to be the number of rows of our theta 1 matrix. Yes, input size. Now the number of the columns is going to be the number of hidden neurons. Yes, so hidden layer size. It is possible to specify it opposite as a transpose. In that case, you will have to change the order here and transpose that. So it is not a mistake that there was written in lecture differently. It is just another assumption that now that matrix in the lecture was considered to have number of rows equal to hidden layers and the number of columns equal to number of the inputs. And actually, I believe, oh, no, it's sadly not written here. No, not here, sadly, but okay, no matter. I had somewhere a similar picture from the same Andrew NG instructor, where it actually specified dimensions of these theta matrices. Yes, sadly we do not have them here. So okay, let us then implement it. Yes, and also as we go, we will also implement the prediction function that is going to calculate the hypothesis. Because as you can see here in the backpropagation, we are going to need to know A3, we are going to need to know Z2, we need A1, A2, basically almost any possible intermediate result, yes, of what we calculate here. And for the prediction, we only need to know this A3 as the final result, yes, without anything else. So we are going to actually make this double function, yes, so one function will output everything and another function only the actual predictions. So we are going to create a new function called feed forward, yes, which is going to return all the variables that we care about, that is A3 as the output, Z3 as the a non-activated output A2 as the output of the hidden layer, that is activated output, yes, and the no, that is here activated, here as you can see sigmoid function, and biased, yes, and Z2 is the non-activated output of the hidden layer, and A1 is actually input with bias, yes, so we need all of them. So first of all, we are going to need to add column of ones, and we need to know how many of these ones need to be in the column. So for this reason we are going to actually read the shape of X. However, we are interested only in the number of rows in X, that is the zeroth parameter, and that is going to be called like M, like in many of our formulas before. The next step is actually adding the column of ones to this X, and that is going to be A1. So we do it as concatenating them by columns and generating the column of ones of the length of M, or that is 5000 in this example, as you can see, and merging together with X, which also have 5000 rows and 400 columns. 400 columns, that is actual pixels for each picture. Then we need to activate it, that is not activate but actually calculate the matrix multiplication, yes, between A1 and theta 1. So A1 and theta 1 are calculated by matrix dot product. Then we activate it by applying sigmoid function and also append the column of ones so that we can send it to the next layer. Just a minute. So similarly as here, now instead of X we have the sigmoid of Z2, right, and this is A2. So we calculate Z3 as the matrix product of the A2 and theta 2, like this. A2 and theta 2. Finally, we apply the activation function. This is the final result. We do not need any bias because we are not going to continue anything, so we skip adding bias, and this A3 is actually our hypothesis. Yes. So sadly, if you want to call somehow like this, let's say hypothesis is equal to feed forward, then it's not going to work. You will actually have to call all of them, yes, which is inconvenient and a little bit abstractive. So for that reason I offer you to create a very simple and easy function called predict that accepts the same inputs x data, theta 1 and theta 2 matrix, yes. So now as you can see, theta 1 and theta 2 are how it's called, unpacked, yes. So before calling this function of the feed forward, we will need to call the function unpack theta, yes, and accordingly after we run it we will need to pack them. Well, not really here, yes, in the backpropagation instead. So what we do here is we actually save all these outputs. However, our function is going to return only the first one. So this way the predict is actually going to have our desired notation. And now we can actually try and run this. So so here I would probably, it would be a very good idea to actually, if you excuse me for a minute, I need to find the weights. So just a moment. I will show you what is expected to be for these But wait a minute. No, actually we do not need it yet, because this is going to be an entire vector, which is not what we want. So we will want to do that. But then again, maybe no, maybe it's still better to actually check if you did this correctly. Yes, so for that reason I'm going to find this short function, not really function, but another data file, which I haven't uploaded to Ortus, but I will right after the end of this video, and accordingly you will have the option to check if so far you have done correctly. Yes, so we need another data file called x4 weights. Yes, well, it's called as exercise 4 from the Andrew course. Yes, so this includes the already trained network with existing theta 1 and theta 2 parameters that have been found. So similarly we are going to copy this fragment. I'm actually going to make a new code fragment here just for this purpose, and we want to load this data file x for weights. This contains theta 1 and theta 2 matrices. However, as I said, these theta 1 and theta 2 are actually transposed, so we are going to transpose them. Theta 1 transposed. Well, these comments actually now not relevant to this what we are doing, and theta 2 transpose, so that now it matches the format that we use in our practical exercise. And of course we want to save it somehow like optimum theta 1 and optimum theta 2. So then if you want to actually now perform the prediction, it is as simple as to call let's say y prediction as the predict x theta 1 and theta 2, and yes, optimum theta 1 and optimum theta 2, I'm sorry. So now we have these predictions. We can actually output few of them. Let's say first, since we also didn't use the training or testing dataset, this is unchanged, so not shuffled, original dataset, which is always going to be the same. And in that dataset it has, well, we can actually see that for yourself, yes, for 100 it's going to have a lot of 9s at the beginning, yes, but our predictions, however, are going to be some probabilities instead, yes. So you can check these numbers to see if they actually match, yes. So for example like this, and of course since now we know that this is digit 9 in question, yes, that has to be the maximum probability here as well as here as well as here. So if you see the similar or even the same numbers, that means so far you have done correctly, and we can go further. So I'm going to remove this as I'm not going to need it anymore, and accordingly let's go further with the backpropagation. Now backpropagation is needed to actually find the error of the prediction and then to find how this error of prediction is actually being accumulated from each neuron. So we are going to go backwards from our neural network, yes, and accordingly find the error for each of these theta parameters. Yes, so basically here, here, here. So we are going to split this error, which is otherwise just one number, yes, into the many subcomponents, and find the derivative this way as well. So as you can see, the final goal here is to specify this derivative with regularization parameter as well, of course, which we will use in our minimization function. So here I'm going to create a new function called backpropagation. Now, and this backpropagation function, like a cost function, is going to be specified inside the minimize function, so it has to work with one vector. Yes, so you cannot specify theta 1 and theta 2 here. It's simply going to produce errors and not work. It only can work if here is you have just one variable. Not really sure if it has to be matrix or not, but it's more convenient to actually organize it as a vector rather than matrix, yes, because it's difficult to merge matrices with different dimensions, whereas vector has one fixed dimension, another can go up to infinity. Yes, so here it has to be packed, meaning that also the first thing we are going to do here is actually to unpack these thetas so that we can calculate them inside. So, but first, before we can do that, we need to calculate how many of these specify what other parameters arguments here are specified which are not being optimized. So optimization will happen only for this theta. Yes, all the other parameters we are not interested to optimize. That includes your data, x, your results, y, regularization parameter lambda, and the number of hidden neurons. Yes, we do not want to change the number of neurons in each iteration. We want to fix it and then let it run 100 iterations to see what is the best solution. Next step is to actually read the dimensions of the arrays. Yes, so what is the size of theta matrix? Yes, so that we can actually know how to correctly separate theta vector into theta 1 and theta 2 matrix. So here we are going to need the number of data rows, that is first parameter of shape x, how many features, that is pixels, do we have, that is the number of columns. We do not really want again to read this because this is just the same, it's the same m as it is here. Yes, so you can actually update it, it's not really that important, but you cannot also miss it. Yes, you have to specify two of them. So I specify this as empty so that I already have m and I don't bother read it again. And this is the number of classes that we have. Yes, so number of unique labels, yes. So that is going to be our dimensions of matrices. Yes, so first theta 1 matrix dimensions is going to be number of columns. No, wait a minute, not number of columns, but rather than that, number of the inputs. Well, no, it is actually number of columns. Yes, that is correct. That would be number of columns. And the second dimension is going to be the number of hidden neurons. Yes, and hidden. Now, theta 2 matrix is going to have dimensions the number of hidden neurons. Well, actually plus 1 with the bias, and here plus 1 also because we add bias as well. Yes, and the number of labels as the second dimension. Yes. So consequently, if you multiply your data with first matrix and then with a second matrix, that all has to go in one flow without errors. Yes, so it's very important to actually follow the order of multiplying here. Yes, it's exactly a1 multiplied by theta 1 and then a2 multiplied by theta 2. if we have the same dimensions as I have now shown. Okay, now we know these parameters and we can actually do unpacking. Yes. So in this function we have to specify the vector that we want to unpack, how many pixels each of your pictures has, how many hidden neurons neural network has, and how many classes our neural network has. Yes, so this produces from one long vector these two matrices theta 1 and theta 2 with the dimensions that I have just shown you, like this. Yes, and colon plus 1 by n hidden, and n hidden plus 1 by number of labels. So this is now available for us. We can actually use this theta 1 and theta 2. Although we specify this as a long vector, now inside of this function we have them in a normal way of theta 1 and theta 2. So as a step of the back propagation, you have to perform the forward propagation. And you also need to know A3, A2, A1, Z2. So we are going to use the feed forward function here. Yes, to calculate all of them for each picture, for the starting from the first by the end, last picture, yes, from this data x, theta 1 and theta 2. Now the next step is going to create empty derivative matrices, theta 1 gradient and theta 2 gradient filled by zeros, and the shape of these gradients is going to be the same as the shape of the theta matrix. Yes, so I'm going to simply copy this theta shape and theta 2 shape to create a new empty filled by zeros theta 1 gradient and theta 2 gradient. Now here it would be better if we could vectorize this. However, this seems to be quite difficult, and it is already quite difficult as it is, so let us then work maybe not so efficient way, and you will see that this is going to cost you some minutes to train the neural network because of that, but we are going to organize this as a for loop. Again, although not really efficient, but it will work. Also, if you wish to, and you can, yes, you can actually try and make this in a vectorized form so that we do not use for loop. That will provide you a big improvement in the speed of this learning rate. Well, not really like that big that it will work in a matter of few seconds, but still significant one. Yes, not that it works too long either. Yes, in this particular case. So first of all, what we want to do is to read from all of them, from A3 all, specifically A3 with number k, yes, and all the others as well. So A3 with number k, A2 with number k, Z2 with number k, and A1 with number k. So A3 is the final result, the hypothesis, the prediction. A2 is the activated result of the output of the hidden layer. Z2 is the non-activated output of the hidden layer, and A1 is the input of the hidden layer. Yes, so we are going to need them all in these formulas now. And first thing we are going to do is to find these delta at the layer 3. Yes, the error of the prediction. So it's calculated as the difference between what has been predicted, A3, and what is indeed in the actual data. So our y is still a vector, actually even matrix, yes, in one-hot encoding. So we specifically say that we want to use only row with number k. Then we are going to backpropagate this to find the error of the previous layer by multiplying this delta 3 with a theta 2 transposed, yes, in a matrix form, like so, and additionally now normal element-wise piece by piece multiplication, yes, not matrix multiplication anymore, with a gradient that is derivative of the sigmoid function of the z2, which we have here. Yes, so we add additional regular multiplication. uh, Furthermore, here you can see that we are going to remove this delta 0, but since we still haven't removed it by so far, we have to fill in this bias, yes, because it corresponds to the bias, for it to have a pair to be multiplied with something, yes. So we are going to remove this first element anyway, so we are going to multiply it by 1, but we could have multiplied it by 0 as well. It doesn't matter with what, it's just some filler so that we can actually multiply it with something, yes. Here, make notice, I use the row concatenation, yes, so I put them together in one row. Now, then, we do this operation, matrix multiplication. However, in Python, multiplying vectors is rather tedious. So, because of that, we are actually now going to convert this vector into a matrix, which we are then going to transpose. And this also needs to be converted into a matrix, but we are not going to transpose it. So, we are going to do this as follows. And yes, and we are going to update our otherwise empty gradient. Yes, so for now it is 0, but now we are going to actually start and accumulate something in that. Yes, so as you can see, theta1 gradient adds to itself and sets to equal matrix multiplication between A1 and delta 2. The delta 2 starts addressing from 1. This is where we actually remove this delta 0. Yes, we do not take delta 2 0, we skip it. And this is a row vector. Now, what we do here is we do new axis. Yes, this command actually converts this into a matrix. So, actually, a demonstration would be nice, I believe. So, if I have an P array, let's say 1, 2, 3, 4, 5, like this, then this is just a vector. It's not a matrix, yes? Now, however, if I do this np new axis, it's, as you can see now, in double brackets. Yes, so that means it is now a two-dimensional array, actually, with just one row. And I can transpose it to convert it into a column, like so. Yes, without these new axes, that would be impossible to do. Yes, so it looks exactly with transpose or without transpose, it's just not working. Yes, you have to add additional axes to make this a two-dimensional. That happens to be for A1 and for A2, and for delta 2 as well. Yes, so however, as you can see here, A1 is being transposed, and then what happens is we multiply new np new axis, this vector, which is transposed like so, a column, let's say with this vector, which is not transposed, as a row. And what happens is we generate an entire matrix, yes, and this matrix is now added to this matrix. So similarly it happens for the second theta parameter. Now that there is A2 and delta 3, now delta 3 does not have this bias, so we don't have to care about it. We do not address it, as you can see here, but otherwise the same. We add axis, transpose A, do not transpose delta. Yes. So finally, what we have to do is divide these errors by m, the number, so to find the average error, that is normalizing. Yes, again I use this notation to make it a little bit shorter, so theta gradient divided by m, And finally, I need to add this regularization term. So in regularization, we skip the first column, yes, so of theta matrix. We simply ignore it, or we can say add it by zeros. So we have to add actually not all of this matrix, but well, if we use notation of Python, then that would be starting from the first column, not from the column with 0, right? And same goes here. In Python this is actually very easy. In MATLAB it was much more difficult to do, so we are lucky that we are working in Python. So, and since if I do it here, it will, you know, try to add this to theta matrix which is bigger than than here, yes, than this sub matrix, we can say, then we actually need to make sure that we add this to the correct range, yes, so we specify this range here as well. So this way we add regularization. Now this is the most difficult part of all, yes, here, yes, because this is actually the algorithm of the training neural network. This error is now propagating back and changing theta parameters. The gradient is actually an update of theta parameter that is going to be used in gradient descent, for example, or in other algorithms, yes. So this way we actually can teach neural network. So the final step is to actually pack these theta gradients into one raw vector, which is going to be used by our minimize function. So we use the pack theta function. Although this is not exactly theta but theta gradient, the function still works the same. It takes two of these matrices and merges them into one long vector, which is then what we were interested all this time along. Yes, so that is going to be returned to minimize function, and minimize function is going to use this gradient to update theta parameters for each layer and for each neuron. Yes, so all that is left before we can actually start training our neural network is to add the cost function. Yes, however, before that, let us actually do additional test. Yes, again, load this pre-trained neural network just to be sure that so far you did correctly and we can go further. It would be very difficult actually to do in a class for everybody, but in this video actually I believe this is much more convenient, and until you have figured out what is wrong you can simply pause this video and continue, and if you struggle and cannot find this problem anyway, you are always welcome to email me or write me a message or ask me in the class when we meet. Yes, so I will be hopefully able to help you, but this is not an easy task to find where is that mistake exactly. As you can see, the code is huge. But okay, I digress. So we have to optimum theta 1 as a theta 1. So actually I will need this once again, so this time I'm not going to erase this. That was a little bit not clever to erase it. Yes, so what I want to calculate now is these gradients. So I'm going to call this backpropagation. However, I need to have them packed, so that would be pack theta, opt theta 1, opt theta 2, and some additional arguments which include x, y, lambda. So that would be x, y. As lambda I will use now 0, and the number of hidden layers neurons is called in our program hid layer size. like this. We do not need this call, and that is going to be theta derivative. This is optimal theta, not just theta. And then I can actually output theta derivative first 100 values. Yes. That is back. Of course, I need to run this function. Just as I run this. Now, this needs to be transposed. That's almost forgotten. And also some more problem here. Okay, that means I might have some mistake somewhere here, especially with all of these bias and reading. Yes. So let's double check. I did copy, however, it's not a guarantee to actually. So okay, I have added bias here for Z2, that is correct. Now A1 delta 2 starts from 1. No, this seems to be correct. And also here regularization lambda gradient. Okay, I'm just going to cheat a little bit, yes, since I can, and I know for certain that this was working, so just to see if this is the problem here or problem is somewhere here. So obviously problem is not in this function, so probably I was spending some time unnecessarily, right, to find where is that problem. Now let's see the dimensions of optimum theta 1 and optimum theta 2. 401 by 25 and 26 by 10, which seems to be correct, and this is also correct. So backpropagation, then kind of difficult to tell why it's not working, but no matter. Let us simply try. Well, I believe we can simply copy this part of code and well, actually I'm going to need this as well. Add a new call block just to see where exactly error happens. Yes, so I specify regularization lambda as lambda 0 in my case, okay, and heat as the hidden layer size, like so. Now this needs to move. So what I hope to achieve by this is to figure out where exactly is the problem, because if this is some major problem, then it's not going to work further, which is not really sure. So okay, it cannot unpack it. Yes, here. Theta. Theta is not defined. Okay, optimum theta. Optimum theta. And call. And heat. And label. Ah, wait a minute, wait a minute. That is because my y is not categorical. Okay, I remember when I was preparing, I ran this same mistake multiple times, so now it's clear. What's the problem? I have to have two categorical here. Obviously, it's not providing the sufficient dimensions, so it's not working. Now it is, however, working correctly. So the idea here now is that you should check these derivatives to see if you have gotten the same numbers. So if you have something resembling these numbers, then it is fine. Also be sure that this is for theta 0 and hidden layers, well, actually you can hard code it here just to be sure that it is exactly like in my example. Lambda is 0, number of hidden neurons is 25. Yes, only for these particular parameters these numbers should be like so. If it is, then we can go further, and accordingly I'm going to minimize this, close this. So we now have backpropagation, and what is left is to calculate the cost function according to this expression with a regularization. Now here were so much indexes that I actually had to, okay, I can see here mistake, that this needs to be actually theta 2, not theta 1. Yes, theta 2. So that I had to actually put that theta index right in the name of this variable. But no matter. Okay, so the cost function is then being calculated just as we did before. So we again have to define the compute cost function just like usually. Then do the same procedure as for the backpropagation, that is read the advanced arguments, that is data, answers, lambda and number of neurons, then read the shapes of our theta matrices, unpack matrices so that we can calculate this cost function now. And as you can see here inside, you need to have the h theta, that is the prediction. So we need to do predict function, yes, from the x, theta 1 and theta 2 that we have now unpacked. We only need to know a3, that is our hypothesis, actually, h theta. Then we can actually start calculating this, yes, by multiplying logarithm of h theta and accordingly adding everything together. So first step I'm going to do is to actually multiply these and these, these and these, right? So accordingly here is the first one multiplication, here is the second multiplication. Now this is a matrix with two dimensions. Now I need to add that by column and afterwards by row, so that out of my big matrix there is only one number left, like so. For example, I have A and P array, that would be 1, 2, 3, 4, 5, 6, like so, yes. So what I want to have is to add everything together. So I need to add summation of A. That will produce me only summation by columns, and then I have to do summation again so that I have just one number, 21. Alternatively, I can use actually numpy summation. Numpy summation, if you do not specify axis as you normally would, yes, it assumes that you are actually calculating by both of the axes, so it's going to produce this just in one go, like so, yes. So we do this now, summation and division by m in additional line here, like so. And finally, we need to add some regularization terms. Yes, so regularization is performed by square, and even more so, first you add for theta1 squares, all of them except, by the way, this is also incorrect here, theta starts with 1 and j starts with 1. Also here 1 and 1. This is called latex, yes, latex, which is mathematical markup language which you can use. Here it is correct from 0 and 0 because here we do not use bias, yes, we avoid using bias. Well, actually I'll make sure how it's done correctly, but in formulas we have this correctly. So we add regularization for theta 1 by adding on top of what we already have summation of theta 1's all columns except first, yes, the columns after first, so not multiplied by squared, and multiplied by lambda divided by double m, just like here, yes, before bracket. So here is bracket and here is bracket. And similarly we do for the theta 2 matrix as well. Finally, we save this cost function, and hopefully we have everything ready to actually calculate to train the neural network. So I save this function, and here I want now to calculate the cost function of this entire thing, yes. So basically all I have to do is to say compute cost. Since I have already run it, it should be fine. But okay, so this is the correct number. I remember it. It's 0.28. That is for lambda 0 and number of neurons 25, the expected number. If you have the same number as well, then that means so far you have created all the functions correctly, and you are almost ready to finish this practical exercise. Okay, so I'm not going to remove this block, just hide it, just in case I might need it. So this cost function is now created, and we go to the final task of running the neural network training process and accordingly evaluating the accuracy. So in the neural network training we do not set theta and theta 1 and theta 2 initial parameters as zeros. Instead we generate them as small random numbers, yes, as follows. So for this we specify some small epsilon value which you can change if you want to, and I would actually recommend you to try different values. But as you can see here, we generate uniform random numbers in range from 0 to 1 multiplied by double epsilon minus epsilon. Yes, same goes for theta 2, except that the dimensions are different, and this plus 1 includes the bias that we need to take care of. Yes. Now we need to pack these theta 1 and theta 2 so that we can actually work with that. Yes. Then we can add some delimiting line, like so, for example, and this is where actually our neural network training is going to happen. So I'm going to use lambda parameter 0, and I would recommend you to start using it also as 0. Then if it works you can change it. Yes, I'm just printing it out and then setting some optimization parameters as additional options, such as maximum number of iteration 100, and I would want to see the result of optimization in the process. Yes, so that how it works. Finally, I'm going to run this minimization function itself. So we are going to save this as a result. This is specific structure. This is the compute cost, the function that we want to minimize. Then we specify the initial theta parameters, which are randomly generated. So actually, if you didn't find a good solution, that doesn't necessarily mean you have mistake. Please try running few more times, because each time it is going to start with different initial thetas, and accordingly maybe you just had bad luck. Yes. Next option is specifying the something called Jacobian, which is basically our derivative obtained from backpropagation. So this is where we specify for our function minimize this derivative that we have calculated ourselves. Now the method that we are going to use here is called conjugate gradient method, CG. Now additional arguments that are specified in the cost function, like here, yes, args, which do not get optimized, include the training data, specifically training, and training labels, lambda parameter value, and the number of hidden neurons. Finally, we conclude that with the options that we have specified, that is number of iterations and the output. Yes, because without this it wouldn't produce a message that it finished successfully and it works. Yes, so let us run everything from the beginning, because I'm afraid something might have, changed something. Okay, so you can see some progress here in status bar, meaning that it works. It's going to take roughly like 30-50 seconds to find this solution. So let us wait then. And afterwards we are going to output these results. It is now longer because I have these variables open. So if you do not need it, I would recommend actually closing it, because this makes things longer. So because of that I have to wait a little bit more, but it's fine. Let it now run. I'm going to collapse all the code fragments that I don't need anymore. Now, as you can see, it has found some solution. The current function, that is cost function value, is 0.04. That is even less than what was before, 0.28 or something. Yes. However, it says that it reached the maximum number of iterations, and it doesn't consider that this is an optimum solution. Yes, it would want to continue, I just didn't allow him. However, I believe it's going to be fine, so let's see the results. Now, first things first, we need to actually unpack this solution, because this solution is also going to be a vector of theta and theta 1 that you need to unpack. So this is contained in result point x structure, and additional parameters are as follows. This is number of inputs, pixels, this is number of hidden neurons, and this is number of classes, 10. So this produces theta 1 and theta 2, our solution. Then I'm going to create a custom function to output the accuracy and plot the how it's called, confusion matrix. Yes, so in this function I specify input data x, input the labels y, and solution theta 1 and theta 2. So first things I'm going to do is to predict values based on theta 1 and theta 2 and inputs. Then I convert from the categories into the actual digits, 0, 1, 2, and so forth. Yes, So I do so for the predictions and I do so for the real y's that I have. Yes. Next thing, I'm going to calculate accuracy by comparing predictions with actual answers and dividing by the number of total predictions. Number of total predictions is the shape of this predictions vector. Yes. Finally, I can also calculate this confusion matrix and picture it by using heat map. Here specifically I specify parameter square so that this matrix actually looks square. And my function returns the accuracy and confusion matrix. Yes. So all that is left is to actually make a text message by printing training dataset accuracy and creating a subplot, because the picture itself is drawn inside of this function. So I only need to specify in which subplot I want it to have. Then I save accuracy of training, confusion of training by running this function. Similarly, I do for the testing dataset. Yes, so obviously for training dataset the accuracy will be high because the cost function is very small. However, how good the accuracy will be for training dataset? Well, we can see that for testing data or training dataset the accuracy is almost 100%, but for training dataset it's actually not that good. And that is where regularization can actually try and help us. Yes. So I'm going to run few more experiments for you here. Yes, so task 5, no, actually I'm going to change the number of neurons as well, let's say to 300 neurons. And well, there is no point in leaving, but no, then again let's return to the 25 and then change the regularization parameter to, let's say, 10. Run it all and see what will happen here with our accuracy. So, in the conclusion, you will need to compare what is the result of the 0 regularization parameter and 25 neurons and whatever is specified for you in the table guidelines here, yes, as individual parameters like 10 and 130 for example, and so forth. Yes, just like what I'm doing right now. So it's going to train. As you can see, training process now is longer and it's going to become even more long, especially if we try to make a convolutional neural network. However, you will be how can I say, surprised to see that it's actually possible to solve the same problem with much better results. Yes. So again, it says maximum number of iterations exceeded. Now you can see, because I added the regularization, it made the solution more general and the training data set is not so overfit anymore. However, this didn't really help our testing data set much. So what I'm going to do is to actually add some more neurons just to see if it will do the trick. So let's say 300 and run it once more. Now you need to realize that once you add more neurons, it's actually going to overfit even stronger, so that will probably will require to increase regularization even more. So 300 neurons without neuron probably, or regularization probably is going to have 100% accuracy for training data set and not so good accuracy for the testing dataset, but we'll see what will happen with regularization parameter 10. And as I said, you can format this right here in Python, yes, to actually look like a report. This is basically how report, I believe, should look like. Yes, well, not necessarily you need these formulas. It's fine if you do not type them. However, the tasks and the results should be mentioned and shown something what you have done here, yes? So, and for example, task 1, you have this picture obtained. In task 3 or in 2, you may output some code. Yes, it's fine to show this code because this is the task to implement this function. So you can put this as a result of this task. Same goes here and for cost function. For task 5, the results are these pictures and accuracy reports. So now it's going to conclude. And on this we will finish this practical exercise, so I will offer you option to play around. You can, as usually, choose freely all the other parameters and from other groups as well, yes, just to see the difference. However, you may also go beyond and try bigger regularization parameters or maybe thousands of neurons, but be aware that this will take more time. The more neurons your neural network has, the longer this training will happen, and this grows exponentially. That is actually the reason why it is better to have neural network like this rather than 100 neurons here. Yes, so it's better to have 50 and 50 rather than 1000 here. Probably better. Yes, I didn't check in this particular data set, but this is option for you. Now, as you can see, this also doesn't help us much. Yes, so the problem here is that these are pictures and the quality of these pictures is not so high. Yes, somewhere it's even possible to see with bare eye that these are a little bit blurry pictures. Yes, so if we were to have better quality pictures, that would also be a lot more data. And finally, as we discussed in the lecture, there is this convolutional neural network type that will easily produce much better result even for the very same pictures that we have here, which is going to be our next topic, yes, our next practical exercise. But next practical exercise, don't worry, is now going to become a lot simpler because we are no longer going to implement everything manually. We are going to call Keras, create, let's say, sequential model, choose the optimizer and run some iterations. Yes, so I will show you in the next week how this looks like, and we will have a small practical exercise where we will solve the same problem by using a Python framework and comparing different types of neural networks, because here right now if I asked you to add one more or two more layers here, it would be difficult for you. You can actually try adding one more layer. This counts as a bonus task for you if you happen to solve it. But, well, this is not an easy task, yes. Now in Python it will be a lot easier, yes. It's not going to be a bonus task there because it's just very simple. But we'll try convolutional neural network and recurrent neural network maybe as well. So if you have any question, please don't hesitate to ask. I will try my best to answer, and hopefully you will find this video record useful for finishing practical exercise. But we will discuss this in class as well, because it is a very major and important practical exercise to actually understand it as best as you can, because this actually allows you to create your own framework. Yes, you do not need any existing programs and libraries. You can even implement your own minimization function by using the gradient descent method as well. So thank you for attention and see you in next videos. Goodbye.